Hello. Probably Rajshekar and then Ayush. We two are there today. So we'll start the session. Um, it's I guess week 8, so it's nice you guys are hanging out and we are there. It's almost 1 month left, so I hope we pass it through and then you guys also have your exams nicely for this particular course. So, do you have any specific questions, or I'll summarize the class, whatever was there in the video session, and then we'll go through the assignment hour. This week's assignment hour is more of similar with respect to the questions that are posted here. So probably you might get some insights. These questions are more of into from the lecture slides only. So there's not much of solving anything or so, just based on contextual information. So that's it. Let me know if you have any questions. Um, if not, then I'll present and we'll start. Okay. Okay. So this week is mainly for modeling of this biomedical system from, so we had 5 of these lectures over here. Last lecture that was spectral and parameterization, I haven't covered that, but it's just basic formulas in there. So again, the lecture with previous with respect to it also, there are matrices and says, okay, symmetric matrices, diagonal values. So you just have to look over and there are different algorithms for the same. So much more of technical information is within the first 3 lectures. I have covered them all, but for the last 2 lectures you'll have to save them because it's just that okay, you need to know that information. There's no common logic or foundation for the same, so it just builds up upon this 340, 41 and 42 slides. So we'll start. So why do we model the systems and why do we need it actually? So firstly, if you had seen that in our previous objectives, we saw initially we saw a CAD diagram for biomedical signal processing, where what we did is we obtained the signal, filtered it, did some signal processing, and then the final analysis of the signal. But now here what's the model over here. So whenever you do something, it's like you have your data set and then you have to see that which trend the data set is following. So you do some data fitting or some curve fitting. Say if my data is some, it's look like it looks similar to as of y equals to x, then I'll do probably some linear fitting. Or if it's something that shows me okay it's quadratic, so I'll do some power law fitting. So it again, the type of fitting what you want to do, it will help you make a compact representation of the data, also will help you find the variation one step closer to the final system state that you're trying to achieve. But from that particular case also, you need to know the nature of the model that you're fitting it over there. So you actually need to know that what all physical parameters are involved, or what particular significance this model is adding after you are fitting it to your model. So it should not be always that okay, I have this code and I have this data, okay, just plot this data and I'll just fit it to the code or the model that I have. So it shouldn't be always like that. You should know prior to hand that okay, if your data is following some and some characteristic features, then okay, so what should be an appropriate model that you fit to it, and what all significant parameters or properties are there of that particular model or its features that you will get after fitting to the data. Only then only you'll get a significant about your information about your data, or else it would be just okay, I did some curve fitting, my r square, that is the goodness of it is around this and this. So it should not be that okay, you just fitted it for the sake of fitness. You should also know the nature of the model. Once you do that, there will be a thing called as bias and variance that we saw previously also, the error estimate. So you'll get some error within the fitting. So it's not always that whatever you're trying to fit with the data that you have, it will give you it's like a nicely accurate 100% r square. It's not always like this, or your root mean square error would be 0. So it there would be some bias, there would be some variance, how much you are trying to do, within what limit you are trying to do. So all that depends upon is like if you're trying to use a model so that to represent your data. So here we'll see two first applications. First is for EMG and the other for ECG. Probably there's one for voice signal also, speech signal. So we'll see that. So if you all remember that for capturing the potential activity of muscle, what we use is the electromyogram. So using action potential of it, we can measure it. So you might remember that, okay, this is how the muscle fiber is made up of. There are the sarcomeres, then we have the Z band, when it contracts and then extends, we have the Z brands. They took over and they overlap over each other, so the thickness decreases. And here these two parameters, these two elements that we have, that's thick filament, that's myosin, and thin filament, that is actin. So these two also play a role in between for the same. So there are also others like troponin, tropomyosin, all of those, but they are, it's like sub part of these. So majorly these two parameters that we have. So surface EMG of a skeletal muscle is nothing but the spatiotemporal, within the space with respect to at which particular instant of time it's happening, the summation of action potential of a larger number of motor units. So this we had a single motor unit. Now there are many such bundle units with respect to in our that made up the entire muscle fiber that are recruited into the action. Now if one such muscle unit is working, then we call it a single motor unit action potential. And then if you see that okay, one such is doing playing its role into, so that would be a very slow process. So people end up in the like calling it as quasi-periodic sequence. So that's quasi-periodic sequence is something like as of our quasi-stationary segment, where we can see how the variation is, but that variation is very slow and precise that you can capture it and do your processing within it. So with the same, what we do is like we extract the, it's like okay, this was your muscle through which you were trying to extract the activity, placing your surface electrode over here, so you got some raw EMG signal. Then you want to try decomposing the signal so that you get the individual motor unit action potential. But you know that while doing the surface EMG, these values that you get over here are not that accurate. Once if you poke needle inside your muscle, and then in order to see the muscle of interest that you are poking, and then you are getting an activity from that, that is something very precise and accurate measurement. But surface potentials also have a lot of noise within it, and you never know that if you're just trying to move or you contracted something, that might also lead to some additional signal in between what you're trying to capture. Again, the interval in between the pulses over here is called as interpulse interval, but this method is no longer used. It's just for your information that people initially also tried decomposing the EMG signal, and then they had this something called as individual motor unit action potentials that is represented as this. So some terminologies to remember that in a normal muscle activation, the single motor unit action potential duration is around 3 to 20 milliseconds. If it's a motor units which are firing, it's 7 to 25 pulse per second. Or if it's the interpulse intervals, then it would be around 40 to 140 milliseconds. So this entire, it is nothing but discrete intervals or the wavelets that you see. So all these discrete waves, and you can actually measure then, okay, how many windows are, how many waves are there within a particular segment of window. So for say for this particular range, how you can do is like this is per second. So 10 raised to 3, because initially it was millisecond, divided by 25, what the number was. Similarly by 7. So from here also you can get an estimation of how many seconds it is playing a role into. So there were other people called Agrawal and then Gottlieb in 1975. They modeled the single motor unit action potential as a convolution of a series of unit impulse response with a basic single unit potential wave. So here it's not that something new has happened, but what they try to do is that okay, if you remember, it's like, can any one of you tell me that what's the principle of a resonant fork? What do? It's like we have two forks, resonant fork, and then we put it to the bench or table, and then we see that it's like it's vibrating at a certain period of time. Now how it vibrates is nothing but that is like we have given it an impulse, we strike it to a surface, we give it an impulse, a sudden burst of response, and then see how the response is. Similarly here also, we are trying to give an impulse response to our system, and then what particular wave that we are getting, so we are trying to modulate that wave. So he himself tried to model this particular system of single motor unit action potential as a convolution series of a unit impulse response with a basic single motor unit action potential wave. Again, keep in mind that this particular wave would be within two certain time intervals or period, points of time. So the same thing, that it is being represented as a convolution of both of them, where this is our impulse train, this is the impulse response of our action potential, single motor unit action potential, and this is the final response that you get is like over the entire period of time. So it's like if we try and do the deconvolution of this particular system. So okay, this is now in frequency domain. Sorry. So here Okay, so this was in time domain, hence we did the convolution. Now, if you convert it into frequency domain, would be additionally multiplication of both of them. So h of say this tau times of x of tau, or say omega and x of omega. Now you can actually find this x of omega. For that, you'll have to divide both of them, take the differentiation, then take the inverse Fourier transform. So in the end, you'll get what your x of t or x of omega was meant to be. So in a way, you can compute it actually. It's like what sort of or what amplitude of impulse response that you need to bang it or to measure this particular train of responses. The next one such application is cardiac rhythm. So you all remember what ECG was. So ECG that was produced by SA node and then traveling towards the AV node and then towards the Purkinje fiber bundle of his and then spreading towards the first atria contracts, then ventricular contracts. So there is a periodic rhythm where first the P wave is generated, then QRS complex is generated, then we have TUV. So accordingly, one depolarizes, the other depolarizes, one depolarizes, the other depolarizes. So this is how our ECG wave was. So here, if you can just see a normal representation of how ECG looks in real life. So this is how, if you go once to doctor and then it's like, if you have a certain, say, I hope you don't have, but if you do have something and then you are feeling some pain and then doctor suggests you to do ECG. So what happens is like they'll place the electrodes here and there, and from the machine, this kind of paper will be printed out. This is more of, it's like previously they used to use thermal print or ink on it. Now I don't know, might be digitalized too. So normally what we see is like something like this. Also the paper is also pink most of the time. So they go get a graph like this on the particular paper, and then you can see that how it's varying with this. So it's not an ideal PQRS that we usually see. It's something like this. Now just imagine that how hard it would be for you to segment the signal, find the peaks of it, find the duration of it, okay, where the signal was inverted, was flipped, all those things. Okay, so while these atrias are depolarizing, what we see, we can also track the arterial pressure tracing. So that is nothing but during the systolic period. So this particular kind of wave, if we segment it within some particular, say, a window or a duration, what we call it as a quasi-periodic wave. Now we, by seeing over here, you can see that, okay, this wave is repeating after a certain period of time. Say, if this is my one cycle, then this cycle is also repeating after this. So this is a periodic wave. Now, if I consider between 0 to 3 seconds, then it can be a quasi-periodic wave. It is also called as a cyclostationary signal. Now, what this cyclostationary signal is, if we autocorrelate the signal with itself, then the signal will tend to be periodic. But a very simple thing that, okay, if the signal itself is periodic, you take the autocorrelation, it would be periodic. It's just that it will tell you that at different instance of time where the energy of the signal is maximum. So we know that each bit is triggered by a pulse from the SA node, and then what P wave is the result of the action potential of atrial muscle units. So basically what we get is from our atrias. Next we have the QRS and complex as well as the T wave. These are nothing but due to the spatiotemporal summation of the ventricular action potential. What it does is that, so initially we had a response from the SA node, then it traveled back to the AV node. So there's always this AV node delay that we play, like we face an issue with. But this particular delay, it will is like this, like when the signal reaches from SA node to the AV node, it's not normally as that, okay, we can't say that the signal is being attenuated at that particular period of time, but what we say is that it acts as a buffer. So it will store the signal and then will help it release it. More of not like a notch filter, but like a buffer. So okay, it stores it and then it releases it. So for rhythmic analysis, if you are just trying to see that if the signal is periodic and then you want to see that at what particular instant what information is getting changed, you can just go and see the beat. So beat is more important there than that of the wave shape. Don't no need to see that, okay, if it's flipped or if it's inverted, if the wave is more longer or if the duration is shorter. All those things are not needed over there. So what you can do is the occurrence of this particular beat or the RR interval. That's the standard method that we have, or which is also called as a time step. So these two are some allowable analysis that we have for this cardiac ECG. So if we disregard the shape and then just look at the beats, that is nothing but when actuating signal plays a role into. So how can we tell it is nothing but a train of impulses, is that at this instant of time something will play, at this instant of time something will play. So that is nothing but a signal that is actuated with respect to an impulse train. That's it. So next is for the voice signal. So voice signal is nothing but if you then excite this particular vocal tract by again an impulse or say random noise, there is nothing but a speech signal that is generated by our vocal tract. So this is how something looks like, and it will vary at some period of time. If I just try and increasing my speech voice now, you might also try wanna reduce your device's voice. So sorry, sound. So it's always like, okay, you see how the signal is being varied. Now in this area also a lot of research is being playing, so that it's like if I tell you one such example in our it's like here in our campus in electrical engineering department, it's like more of biomed. People here are working with sensors. These are called as fiber Bragg rating sensors. So what they do is like once the wavelength of this particular sensor changes, that is called as the Bragg wavelength. So when this wavelength changes, and there is a change in light transmission, and from that you can see that okay, how much variation was there. So people in our lab are trying to see that how they can utilize this kind of sensors in order to make transducers, whereas in people from other labs they are trying to see that how they can modulate a speech signal using the help of this sensors. So these sensors are like this much small in micro range or nano range. So their fiber Bragg is also that sensitive that even if you break it a little bit, your 50,000 or 1 lakh rupees is wasted. Then your PI again has to go through all the procedure and has to buy or purchase another one. So there is research going on into this area also, because nowadays we have specially abled people who face a lot of issue while speaking. So we need to see at all perspectives and then develop our methodologies, advanced technologies accordingly. Just an example. So what happens over here is like each and every person has a different uniqueness of voice. So this particular vocal tract, the shape of it will vary with respect to time. So it is nothing but a time varying process. So at once it's like, say if I'm suffering from cold and cough, my voice would be different. If it's something else, it would be different. If I have to speak in a very smaller class, I'll speak very less, it's like very lightly. My amplitude will also be lesser. Whereas if it's something I have to give a presentation in front of my lab, it would be, it's like I'll try to make myself that audible that okay, everyone is able to hear me out. So however smaller interval that we do usually, then it can be taken as a quasi-stationary. If it's a slow variation in between the different phenomena that we are uttering, so we say that within the quasi-stationary period, we can consider or take it as an assumption that it's a slow variation. It can again modeled as a convolution of the vocal tract response with the glottal pulse strain. So we initially saw that what glottal pulse was, that something that originates from the glottis, that's it. And then the input may be modeled as a random noise for the unvoiced sound. So if you don't have anything, so if your sound is not being given a pitch or a frequency to it, then that kind of sound is called as unvoiced sound, and then the input for that particular kind of sound can be a random noise. So I guess till here only we had these three examples, that is this EMG, the other was ECG, and the last was voice signal. So do you have any questions on this? If not, we'll go to the next part. Have any questions? Probably. I'm audible, right? Microphone. It's like I can see one of you turning your mic on, but I'm not able to hear you out.
Yes, ma'am, you're audible.
Oh, okay, okay. So do you have any questions like Ayush, Meg, and Rajashekar?
No, ma'am.
No, madam.
Thanks. So we'll go to the next part. That is our point process. So what happens in point process is essentially the same, that we have a response and then we club it or convolve it with the filters in initial input impulse response, and then we get a Y of t. So here we see that okay, so from here I've used all the slides that sir has given in his lecture. It's just to maintain it's like homogeneity here and there. If you want to see that, if you there's two books, one from the it's like I forgot the title of the book, but it is same as the author is Rameshwaram, something like that, and the other that was introduced in the last week. So there are two conventions in the like in between these two books. So if you just see, and the formulas, everything is same, but then if you're sticking with this one, then better to stick with this one. Everything's same, just the terminologies will vary. That's what the point. Hence, I also use this. Okay, so back to it. So if we let the time interval between ith impulse as well as the previous as that of tau I, so what this tau I essentially is that it can help us give the time of arrival of the ith pulse as tau I is equals to multiple summation of all independent samples of this tau I. Here, if we see that tau is an identically independent distributed function, so if that's the case, then we say that okay, the mean we have the mean as mu and omega is like as sigma square for all intervals. The time stamp is greater than 0 and the index is greater than 0. Now why so? Because we can't say that okay, if it's a negative time period, these are the signals from the past. Even if it's from the past, it would be just your original signal that is delayed back to some points, so it won't be ever negative over here. So the time of arrival for this T ith of pulse would be nothing but sum of all these ith independent variables. Their mean and variance again can be represented as this has a mean and variance of mu and sigma square. Then if all of them are in it's like independent and multiple of each other, so it can be I mu and then I sigma square. So that's like that. Next is that if you know that okay, this is your time arrival, and then if you have to represent it as in with respect to Gaussian PDF, then this is a normal actual form. So how actual form of Gaussian PDF is nothing but 1 by square root of 2 pi, then sigma we have, and then exponential of x minus mu by sigma square. So this is how the Gaussian PDF is being described. But then over here, if you have your this time of arrival also given to you, and this is also a random variable with a Gaussian PDF, then you'll have that 2 pi, then it was this Ti was a multiple of your all tau interval, so it is I sigma for the same, because sigma turns is to I sigma, exponential of this. Now here we have x minus mu ka whole square. So what x is nothing but our random variable here Ti, and then minus mu is nothing but I minus mu whole square divided by sigma square. So what are sigma is nothing but I sigma times 2 is the interval multiple over here. So this is how the Gaussian PDF is then being changed or modified with respect to this particular variables for which we are trying to define. Okay. So what we see is that the input point process this x of t that's represented by this train of impulse that we have. Now the Fourier transform of this particular point process can be given as, so you know the definition of Fourier transform, it's nothing but the signal times exponential e raised to minus j omega t. So this is quite obvious, right, that if you have a Fourier transform of an impulse with respect to an exponential or say some other signal, then you will only get the output as t is equals to ti, or where the impulse is being defined. So here if you do your impulse, if you want to find that where the impulse is giving its an output, you'll just try and see that okay, t equals t minus ti equals to 0, so that is t equals to ti, hence it's being defined for, it's like for this exponential but at ti. That's it. So this is your Fourier transform of this point process, that is xt, as nothing but multiples of this exponential signal. So if that x of omega being a function of random variable is a random process itself, because it was initially defined using a white noise, where white noise actually itself is a randomness, involves some randomness, then the mean value can be obtained by taking an expectation. Similarly, variance can also be obtained by taking a second order of expectation. So here what they did is like took the expectation of this our exponential signal that we had. Now how to elaborate this would be is like you have your expectation would be nothing but multiple intervals of the probability distribution that you had at each and every it's like timestamps. So then it can now integrate the formula of the Gaussian PDF here. So this is nothing but accordingly you can just substitute the values. Now if you just try and change ti minus I mu as r, where r is just a temporary variable, what we get is something like this. So it's this constant is same, this constant is same. What you have here is something like this. So then how to evaluate this particular integral? So for that, we use a property of the Fourier transform. So what they have used is that exponential of minus t square by 2 omega square. Okay, so they know that, okay, already the Fourier transform of this exponential is something like this. Now for that, what you need to do is like go and see the time and frequency response for the properties of Fourier transform. So you'll be able to see that, okay, how do we get this? Because it is nothing but essentially the scaling property and then changing this particular variable to this. So you'll be able to get the square root of 2 pi. So we get this expectation and then we change it. So this is how our mean of the signal is essentially. So then if the ensemble average Fourier transform of the output signal can also be given as, if this is of the average, then this would be also the final. Is like ensemble average is nothing but of all frames or of all intervals of time, where this is nothing but the Fourier transform of our impulse function. So next is parametric system modeling. I guess this is the last one. Then we have autocorrelation. Probably that's it only. So this is something new probably to you guys. I don't know if you have learned it so far in your it's like curriculum for now. So how there's it's like probably you are it's like familiar with this term called as difference equation. So if you know the first are the estimates of derivation and integration. How we do was is like limiting something in an x of say some variable plus h minus h divided by h. So that way we can get an first order it's like estimate of the derivation. So here also, if we assume it's like our system to be linear and time invariant, so this particular kind of difference equation is given by this. Now here, this is your input signal, this is your output signal. Again, this corresponds to the moving average. This is the gain of the system. This p and q variables over here are the order of your system. It doesn't really matter what the order of your system is, but again, if you are trying to do some filtering with your system, and then if you are having some multiple networks or layers within your system, then this order might matter. But if it's for a single valued, it won't matter that much. Or even if it's for say for 5 to 10 samples, it won't matter that much. And then this kind of variable ak over here, it's a variable of autocorrelation coefficient. So here, so not correlation, autoregression coefficient. So this is for the autoregression part, and this is for the moving average part. So there is something, a newer technique here that we have is called as ARMA system. So what this ARMA system is nothing but autoregressive moving average filter or a system, where similarly this x of n is nothing but a white noise that we had previously also. Okay. So what observations can we derive from this particular model is that it can be viewed as an IR filter due to a feedback loop. Okay, let's go and see where is the feedback loop over here. So you are essentially trying to take the past values and then you are trying to update the new value based on the past value. So essentially you have a signal from where you can see and modulate it, that how can I change my present value with respect to how I had my past values. So here we have something. Then since we had something and we have a measure of the past values and how we are changing it, so it indicates my system has some memory. Now it also indicates that the present output can be predicted as a linear combination of the present and a few past input and output values. Hence the model is also known as the linear prediction model. So how the linear prediction model is that, now it can also estimate based on the past is like past input value as well as the past output value. So this is your past output value, this is your past input value. So accordingly you can change this and can modulate your present value. So this kind of it's like this auto regression moving average filter is kind of nicer, but it's more trickier also to implement it. So I did my project with one of the professors from here. He's Professor Krishna Miyapuram. So I worked with him on EEG data. So what we did is we were trying to see that if we can measure, if we can detect the seizure before time. So the onset of the seizure. So what we were is like, if you have a seizure or a tremor, that particular period is called as an ictal period. A period before that is called as pre-ictal period, and a period in between them is called as an interictal period. So what I was trying to see is that if I can see some characteristic differences in between the pre-ictal and the interictal period, so that I can try and see that when the ictal period will start. So that was my entire hypothesis. I ended up using this ARMA model, and then it was first time for me to do Python and all this coding for that, because I'm normally proficient with MATLAB. So tried and went on with that. And then I was able to do something. But then you all know that, okay, machine learning, deep learning, it's all about how your loss is lesser and how accurate your model is. But people never really tried seeing that, okay, how much you're able to do or how much it's in real time. So this ARMA in a way helps you because it gives you a real time estimate of your approaches. So that's kind of nice. And it can also, so for here we are trying to see that our output, our input here was a white noise, although it was random. But for the sake of here, or for the completion, we are assuming that it is a deterministic signal. So we have an idea of everything about the signal. So in my case that I gave an example now is that, okay, I knew that when the ictal period was, when the starting and ending period, the onset and offset of that particular period was, so that I was able to do some estimates on the pre-ictal as well as the interictal period. So that is how somehow that we are here also trying to see that as like we are trying to force it that the signal that we are having is a random white noise signal, but in a way it is a deterministic signal. It's like we know everything about the signal, and the signal can be splitted up into some determined equation and set of values. Okay. So if you try and apply to this particular equation, Z transform will essentially get is nothing but something like this. It's like something varying with respect to the moving average coefficient filter with respect to your auto regression coefficient filter. Here, both of them will are equally applicable in time as well as in frequency domain. And then it can be characterized based on all the positive values, not the negative values, for the sake of time being positive. That's it. And again, P and Q are the order of the systems or the values that you have. Suppose if I try and build up a CNN model or a basic which model, let's say only CNN model. So in that particular model, I'll see that, okay, how many layers I want to add in my model, right? So how many times, so what CNN is? CNN is essentially convolutional neural network. So what we do is that each and every layer, we apply convolution within a particular set of ROI and between each and every pixel point that we have. So essentially everything is being like convolved with each other. So now here, how many layers or the networks that I'll add would nothing but define the order of my system. That was order over here. But if you have something as filtering or say, it's like some order kind of filter. So it is like normally people say, okay, this is third order Butterworth low pass filter or fifth order or seventh order kind of filter. So what they have there is like the stage is repeating itself that many period of time, but the feedback is changing at each and every stage. So accordingly you can also define the P and Q in that context. So again, the transfer function can also be written in the form of pole and zero, so the poles of the system and zeros of the system. So there are multiple ways to write. People prefer this way, or like this way is more convenient because you directly take it up from this equation, whereas if you want to try and then remember this particular part, it's also fine. So this is the autoregressive or the all pole models. You do not have any zeros in here. So it is modeled as a P previous output values and the present input sample as. So if you have input Y of n, it's defined with respect to your original signal at like present signal, that's G of a present input signal with respect to the gain of the system. Gain doesn't matter that much because normally you do not add a gain to your signal whenever you are acquiring data. It's essentially or inherently in a way you have an amplifier for the same. So but still people have that particular factor in there so that no such problem occurs, and then you can modulate it or tune it if you want at some point. And then you have the past values of the output with respect to your autoregressive coefficient. So you can again take the Fourier transform of it and you see the similar equation we get, but we do not have any zeros over here, hence it's called as an all pole model. So within this all pole models, similar people have tried using it for EEG signals, for PCG signal, where the input is unknown, but what you want is like what will occur in the future, or what's actually trying to come in into that specific period of time, what can be predicted, that you know somehow. So from there also you can, the current sample only can be predicted using the past output samples that you had previously. So this tilde is being added, so because it tells you a predicted value, that is nothing but an approximate of it. So it's negative because you're taking it off the past values, and you also remove the gain of the system as well as the present value of it. So how do you see that if what you're trying to achieve, it's essentially the same what you will get, and when you acquire at that time instead of time, so you measure the error in the predicted value. That error is also called as a residual when you measure it like this in a way. So if you have your original output signal minus the predicted signal, so this would be y of n plus of this particular factor over here. So same way. Okay. This right. Huh. So then what we do is like the corresponding signal flow diagram for the same. So I hope that first till now that you know how to make this diagrams, is that how many times the signal is being delayed, you add this v minus 1 ka block, and then what are the coefficients for the same, so this get multiplied to it, and then finally we add all of them. Now here, since it was for two processes, so first we had our y of n that is being added to the error, that is, so error is equals to y of n plus, and then it would be all these factors addition and multiplication, whatever you feel, and then this is for the y tilde n, so that is subtracted, so minus minus would be plus, so in a way you get the final error that you have. Okay, so if we have I guess it's the same thing, given y of n, the parameters can be calculated by minimizing the mean square error. So the total square error is given by, okay, so if you have the mean square error, how do you find the total square error? Is the square of the mean square error. So that is essentially the same thing, but here keep in mind that you do not try and stuck into a local minima. If you try and get stuck into a local minima, any such method that you try to use, say a gradient descent method, well, it's like where you are differentiating it again and again and again, but you're never trying to reach into, it's like you won't and never reach into the global minima. So that's a point where you need to ensure that the derivation of your error with respect to this particular total square error with respect to your autoregressive coefficient should be 0. Now, if it's 0 at that particular point, keeping the indexing is all positive until the order of the filter that you're playing a role into, you can suppose that what you are getting is not a local minimum, but it's a global minimum. I hope that was clear. That instant was something a loop in this all equations, but I hope that point is clear. Okay. If you have, you can ask me any questions. Okay. So it yields the following P equation. So you add summations here and there, then you have input as like the present output with respect to the past output. Similarly, you have this coefficient, so we added summations here and there. So what you have is that now we have the equation in y of n for this p unknowns. It's like for the p unknown order that we do not know that what the order of the sequence would be. So this set is also known as a normal equation. Now if you solve for this particular set, the minimum total square error can be obtained using this particular equation, where you essentially add it for the present output and then you just take the output of the previous state that you had. So that's it. So it's nothing but, so autoregression also turned into autocorrelation in a way. So it's nothing but autocorrelation sequence. So the range of minimization can then be taken as with a negative infinity to infinity. Initially, what we have is nothing but the autocorrelation sequence of y of n. That is nothing but the signal with respect to the past output value. So what you saw initially also, that is nothing but autoregression also. So when y of n is available only for a certain interval, say if it's for 0 to n minus 1, that's, it's like if you take from 0, it's n minus 1. If you take from 1, it's n. Same. So the autocorrelation estimate has to be modified accordingly. Now, the values, if you index it in a similar way and you try it, so if it's from I, you have to do it n minus 1 minus I, and this values over here. That's it. So this equation, if you try and add some value, is like if you try and manipulate it in a way that you had for autoregression, add the autoregression coefficient over here. So you can also, by doing autocorrelation, you can estimate the values of, yeah, is that autoregression parameters, because performing autoregression is kind of tricky in real-time data. But if you have an idea about autocorrelation, its knowledge of that is sufficient in order to compute these parameters. Again, if you try and scale it or normalize it, it won't give you any like better outcome. It's better, people say that do the normalization before doing anything to the data, but scaling the data or saying that okay, I'll whatever I do, I'll just for initially I'll take my data between 0 and 1, then only I'll do the further processing, would do no good. It's essentially the same thing. Okay, so this is how we have the total square error then. So we just changed all the parameters that we have with respect to the autocorrelation coefficient of the signal itself. This was at 0 and this is at that particular instant of value, or the order of the filter, or say the autoregressor. That's it. So till now everything was deterministic. We saw that the signal had those values, but it's also that okay, the white noise was random, so because x of n itself is white noise, so for that the equations will change. We have set of matrices, that is a Toeplitz matrix, and then that is a symmetric matrix. The diagonal values add up, the inverse doesn't exist for the same, so these values that we have over there, so it's just that, and then people have given certain algorithms, so you just need to remember certain steps. Till here what was something that okay, was something that I can explain you, and if you do not able to recall this all formulas, you can just understand the logic behind it. So there the part is something that okay, you need to know how it's being done. If it's asked, you need to know a particular stepwise formulation for this game. So I guess that's it was for this autocorrelation and parametric system modeling, also for this point process. Have any questions? Ayush, you're not audible today, I guess. Because last time also you tried to unmute yourself, but you weren't audible. Then Meg or someone said that, yes, probably. Okay, any question?
No, ma'am.
Okay, Srinarish, it's fine.
Yes, ma'am.
Okay. So I guess that's it. So last two lecture slides are normally the applications on the same, so I haven't covered them. You can just go and have a look because it's just the same. So this, if you have actually doubt within this particular part, it's essentially all the formulas in there. No such context or new methods have been covered. So just a brief of an advanced method. So if you need, we can cover it in the next week. If not, then we can just go with the assignment questions then. So is it fine, or you have any questions now? Ayush, you're trying to say something?
Ma'am, I have a question in assignment. I will ask later.
Okay, okay. Okay, so we'll do assignment task. I hope you three will be active during that time. If you don't even know the answer, it's fine. Even today, I was in a kind of hectic schedule, so I didn't get much time to prepare. We'll just go through the assignments together. So the motor unit firing rate is expressed in terms of pulses per minute, per second, Q frequency, or none of this. What, which one?
Option B.
Yeah, yes, in pulses per second. Then probably this is something to remember. So in normal muscle activation, the motor unit firing rates are in the range of, I guess this was 7 to 25, right?
Yes, ma'am.
Probably it was 7 to 20. Yes. Okay. Then if x of t is a pulse train, h of t is a single unit action potential, then y of t is what? So we saw that, okay, it was what? Was it a convolution, addition, multiplication? And then if it was a convolution, then what its limit would be?
Option
Ma'am,
A.
option A.
Yeah. Matrix is a Toeplitz matrix. So I guess this was there in the last or last to last lecture slide. If it's symmetric, they along any diagonal that are identical, the elements,
Option A.
or it's yeah, yes. Then the Fourier transform of a point process is given as this. So this will give you what? It's like, what would be the Fourier transform? We, I guess, saw what the Fourier transform can be. So what we do is we write Fourier transform x of omega as x of t times e raised to minus j omega t. Now this e raised to minus j omega t, x of t is summation of I equals to 0 to n. And then we have delta of t minus ti. So this will exist for ti impulse. So what will happen to e raised to minus j omega t?
Ma'am, option D.
Option D. Yes. Yes. Okay. So this is something I guess you'll have to write and do, but it's based on this particular y of n formula only. So the autoregressive moving average system is given by this formula that we saw previously also, and the coefficients are given also. Gain factor is 1. Find the causal output sequence. So causal is nothing essentially from 0, the positive side, using the above ARMA system for the input signal as 1, 2, 3, 4. So note that the signal values outside this interval is 0. First sample in both input and output is at n equals to 0. So this is at n equals to 0. So take this hint in mind. So the first sample in both input and output is at n equals to 0. And then accordingly try to figure it out. Because at n equals to 0, you have in value. Anything that's not given over here, assume it as 0. You'll have a couple of equations and then try to eliminate the equations. And hence, any guesses? Or you're trying to do, just give me a hint if you're actually trying to solve.
Ma'am, I think all options are incorrect.
What you did, tried fitting the options.
Ma'am, actually, when we will put n equal to 0, then in the equation y of n minus k term will be y of minus k, and x of n minus l will be x of minus l. And it is given that the first sample in both input and output is at n equal to 0. Then y of minus k and x of minus l will be 0. Then y of 0 will be 0, but in none of the option it is given 0 actually.
But y of minus k and then x of minus l, do you have the values for that? No, right? And it's essentially x of 0 and then y of 1. Negative 1, say. See here.
Actually, ma'am, it will be y of minus k at n equal to 0. And when we will put k equal to 1 and 2, it will be on the negative side, y of minus 1, y of minus 2. And it will be 0 because it is a causal system. It is given that the first sample in both input and output is at n equal to 0. Similarly,
Yeah,
in case of minus L also.
yeah, here. But okay. Just have a look. So if you have this additional sequence, just split it up as negative of a1 times y of n minus 1, a2 of y of n minus 2, and then similarly, your next sequence is b0 times of x of n plus b1 times of x of n minus 1. So if it's for y of n, here, this part, it can be it's written as y of 0 and y of 1. Now add the values accordingly there. And then for y of 1 we had, y of 2 we have, y of 3 we have. Try digesting this for some time. So what we did essentially is that, okay, we see that for how many terms we can get this value. This is actually from 1 and 2. So just as try, it's like just go and put these values, initialize it there into this term. This is for 0 and 1, add it over there. Now see that for where you are actually starting the sequence. Essentially, the signal is 1, 2, 3, 4, that is 0, 1, 2, 3. So this is also been defined from 0, 1, 2, 3. Now try and add those values and then we'll be able to see. So for n, you have an estimate over here, n you have an estimate over here. This constants you know already. Gain is also given to you. Then x of n also you know, x of n minus 1 you can also know. It's essentially 0, this part. But if you try and it's like what they say is that if initially it would be 0, negative 1 would be 0, but then next you'll be having some value. So for x of 0, it says, I guess 1. Then you have an x of, this is for x of 0, then x of 1, x of 2, like that. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Next, which of the following represents an autoregressive model? Okay, this is just some formulas. Yeah, 1 B gain.
Option.
1. Which one? D.
C.
I think it's A.
Gain of the system. Why do I feel that if it's all of the above? Oh, it's A. Okay. So this was not given anywhere. We saw this part. We saw this kind of behavior. We also saw that we can split it as the gain of the function and the present signal. So, okay.
Ma'am, but the
Yeah.
C1 is the ARMA model. So if they're only asking for autoregressive, it would be.
Yes. Okay. Yeah, yes. Nice. Then, because the following statements are true about the parameter estimation of the autoregressive model. Okay. So as it tends to 0, the model's autocorrelation and PSD becomes identical to this. As it tends to infinity, they become identical to them. The order variation does not cause a change or none of this. Okay.
Option C.
As it tends to infinity, it becomes identical to the signal and yeah, yes. So it's okay, last one. For modeling of values in the spectrum, which is more appropriate? So we now only saw that, okay, if we want to have a minima less than 0, if we want to estimate our minima, what we try to do is see if it's the derivative falling into. So that was for which technique?
A option.
Yeah, yes, for autoregressive model. That's it. Sorry. Moving average model is most appropriate. No, autoregressive should be the answer. Moving average. Probably I selected the wrong key here. Autoregressive model is the most appropriate. Yes. Thank you. If you have any questions, let me know. You had a question, right? We'll open that. Yeah, yes. Which question?
Ma'am, question 4.
Okay, is incorrect. For an ortho process, autocorrelation may be computed as time average. Knowledge of this is sufficient to calculate this parameters. Okay, autocorrelation of the input to filter is this matrix. What do you feel?
Ma'am, first option is correct. It's 100%. Ma'am, in second option, this statement was given by the sir in the PPT. But actually, ma'am, I have a doubt that it is for ARMA model or auto-regressive or all-pole model in second
Okay,
option.
for the last, yeah, I guess so. Where you got it is the accurate point. Was for the ARMA only. Computed as modeled as this. We went too far, huh? Here it's not there, right? Wait. An autoregressive process, ensemble average. Okay. I saw that, right? Autoregressive or an all-pole model. What indicates this? Now this one. So this is an estimate of accordingly. So this is enough to
Yes,
calculate
ma'am,
the
first observation.
AR parameters. So that is for an. Now let's see what the equation was. There we tried differentiating the equation. So this equation is for your this model. So accordingly, you're trying to manipulate it and then you're trying to estimate.
Ma'am, actually, auto-correlation method and covariance method were for the AR model, not for ARMA model. That's
Yeah.
why I'm in doubt.
Okay.
And ma'am,
And then the
in
C
C
option.
option, yes, ma'am. In C option, ma'am, I have a doubt that. 1 second, ma'am.
Till he takes
Yes, ma'am.
his
In
time.
C option,
Okay.
ma'am, in C option, अबे कहाँ चला गया? Yes, ma'am. This is written. The matrix in left hand side is autocorrelation function of input to filter in case of Wiener filter. So
Yeah.
by this, we conclude that the C option is given for the Wiener filter. So I have a doubt that, ma'am, in Wiener filter case also it's a Toeplate's matrix or not.
Oh, so from where you initially started? So what did you actually give it as an input when you saw that, okay, the final response resembles to a Wiener filter?
Yes, ma'am. The first matrix is for the autocorrelation function ACF.
Yeah, that's it.
Option will be option B because it's for AR model, not for ARMA.
I can't say. It's up to you. Okay.
Okay,
You have
ma'am.
any other questions?
Yeah, I got it.
Meg, you have any questions?
No, ma'am.
Okay, then. Thank you. Thanks for joining.
Thank you, ma'am.
Thank you.
Ma'am, I have one more question.
Yeah.
Ma'am, since exams are approaching, ma'am, I want to know the technique of studying, ma'am, this subject. Because, ma'am, I was making notes throughout the lecture, and I have two thick classmate registers full of notes, and it's very difficult to, ma'am, mug up and
All this
learn all the formula theory. So, what is the technique of studying this subject?
For NPTEL courses only, probably I'll say that first, if you're trying to do all the assignments and you pretty much have covered, say 50 to 75% of it. Now, next 50 to 70, 25 or say 50% total would be towards your conceptual knowledge. So most of numericals won't be asked that much. If they are, then it would be very simple like we use now only. But if there are something more than that, so it would be directly on the conceptual information or something that's not actually from the slide, but okay, you can see it, but it's like the instructor hasn't actually written it in those words. So have a look at some diagrams, see that what the diagrams are actually meaning. Have a look at the book, but I don't think so. It's like NPTEL has a strict policy that something there's there in this lecture slides, they'll only ask questions from there. So if you go through the lecture slides and questions, it should be enough. you'll be able to cover it pretty much nicely. It's like above 75% to 80% would be nicely done.
Ma'am, I have heard that NPTEL exams are mostly made from the assignments. Is there
Yeah,
something like this?
yeah, that's why I said that. If you are, it's like even if you don't study for the entire period of time, but you just do this assignments nicely and you have a thorough idea that why this particular question is like this, or if there's some another question to it, what alternative answer can that question give to that answer. So that will also help you prepare in a way. So that will eventually help you pass. But even if you want to score nicely, it's better that if you go through all the lecture slides and then have a thorough idea that what's going into. More of is if your contextual knowledge is nice and brief enough, then shouldn't be a problem.
Ma'am, because I have, ma'am, analyzed some of the questions of the assignment. Ma'am, they do is that, ma'am, like sir have given a statement in the class. They will, ma'am, remove 2 3 words. Like first question is SMUP is a dash signal. And
Type
ma'am,
of
if you are knowing the statement that it is a quasi periodic, then only you will be able to answer that.
answer that. Yeah, yes. So that's something that if you have looked up at the slides and then you know the assignment questions, then only you'll be able to stick on it. Now if people who have directly went to the class and then okay, they just see that if this is something for quasi periodic and not for a periodic or pseudo periodic, now they don't know the difference in between both of them, so they will be confused at that time. So it's a kind of a easy question for the ones that who know that okay, what a quasi periodic signal is. And even if you don't know, you know that we do our processing on quasi periodic signal, we do our processing on stationary signals. So that's a kind of logic that you can have it in there. But if you don't know anything, then it would be a kind of tricky situation for you.
Ma'am, this means that if we do all the questions of the assignment, if we mug up all the 10 questions into 12 assignment, that is 120 questions. Then, ma'am, I can score nice.
But if you mug up, I can't say. But yeah, if you know the concepts nicely and thoroughly, then shouldn't be a problem for you. So because you have been consistent, you have solved all the assignments so far. Now just the case is that you need to remember this basic details. For see, if you have also noticed, most of the formulas aren't asked that much. If formulas are also there, then you'll probably see. Now here we saw some formulas were there, so you probably see some relation in between those, that okay, how it's varying or which one can be. Now, as Meg also pointed out, okay, here it was autoregressive, here it was moving average. So if this is autoregressive, what can be? So if it's up to the equations, it can be like that. If it's not, then it's essentially more of this as like long questions and all. Exam is, I guess, 3 hour exam, right? 3 or 2.5 hour exam.
Yes, ma'am, 3 hour.
I'm also giving an exam for this course.
Ma'am, have you analyzed previous year exams, like what they asked? Were they
No, no, no.
related to the assignment or there were new questions?
No, first time. It's also my first time. It's like TAing this course and then taking this course is also first time. If I get anything, I'll ask the
Okay,
other
ma'am.
TAs and we'll let you know in the next week or so. If they have an idea, I'll let you know. We'll stop the recording for that first.
Yes, ma'am.
Okay, then we'll see you. Bye bye. Thanks for joining.
Okay, ma'am. Thank you, ma'am.
Thank
Thank you,
you.
ma'am.